Hello guys, let us continue our discussion of paper 2. We'll start from question 3 onwards. So let us read the question. As shown in the figures, a uniform rod O dash of length L is hinged at point O and held in place vertically between two walls using two massless springs of same spring constant. The springs are connected at the midpoint and at the top end O dash of the rod as shown in the figure 1, and the rod is made to oscillate by a small angular displacement. The frequency of oscillation for the rod is F1 in the first case. On the other hand, both the springs are connected at the midpoint of the rod as shown in the figure 2, and the rod is made to oscillate by a small angular displacement. Then the frequency of oscillation is F2. Ignoring gravity and assuming motion only in the plane of the diagram, the value of F1 by F2 is, we have to find out the value of F1 by F2. Now, two arrangements are given. The first arrangement is this one, where this rod is connected to the wall via two springs of same spring constant K. One spring is connected at the top end and another spring is connected at the midpoint. Let's assume that spring constant is K, and in the figure 2, that is our second case or second arrangement, the same rod is connected to the wall via two springs, but in this case both the springs are connected at the midpoint. Now let us assume the length of the rod to be L, and this is of course L by 2. This is L, this is L by 2. This is figure 1, this is figure 2. Now both the rods are in equilibrium. Now small perturbation is given to the rod, and that perturbation that can be given to this rod only is the angular displacement. So both this rod will be moved or will be perturbed from their equilibrium position by small angular displacement of, let's say, theta. This rod is also moved by small angle theta with respect to the point of oscillation. This is the point. With respect to that point, the entire rod or entire system will oscillate. Let us see the first case. The first case, when the rod will be displaced by small angle theta anti-clockwise, let us assume anti-clockwise. So then this spring will be compressed and this spring will be extended. So this extended spring will try to regain its original shape and it will give the force to the rod in this direction. Similarly, this spring will be compressed and it will try to regain its original shape and it will give the force in this direction, that is towards right. Now what is that spring force? For the top spring, the spring force will be K into the extension of the spring. And what is the extension of the spring? L into theta. This is L into theta. That is the extension of the spring from the equilibrium position. So K into L into theta. Similarly, for this spring, the second spring, what is the compression of the spring? That is L by 2 into theta, because this length is L by 2 into theta. So the spring force will be K into L by 2 into theta. These two forces will generate one torque that will ultimately try to restore the equilibrium position of the rod, and it will oscillate with respect to the equilibrium position both sides. Now what is the restoring torque that both of these forces will generate? In the first case, restoring torque, for the first case, this force is acting at L distance from the point of oscillation, that is this point, the fixed point. So the restoring torque is KL theta into the distance of the force, that is L. So KL theta into L, of course clockwise, plus this force will also create clockwise torque, that is KL by 2 into theta into the distance, that is L by 2. So KL by 2 theta into L by 2, and that is the restoring torque T, and T I can write as I minus I theta double dot. So theta double dot I can write, it is minus of KL square plus KL square by 4, that is 5 KL square by 4 into theta by I. So this entire term is actually the omega square or the angular frequency square for the first case. So omega 1 square I'm considering right now, that is 5 by 4 k L square by I. Now omega I can write 2 pi into f1. So I can write omega 1 square is 4 pi square f1 square, that is equal to 5 by 4 k L square by I. Now we'll see the second case. Now we'll remember this or box this, and then we'll see the second case. In the second case, if the rod is of course displaced angularly by small angle theta, then this spring will be compressed, this spring will be extended, this spring will be compressed by how much amount? L by 2 into theta. So the spring force will be in this direction, and the amount of force will be K into the compression of the spring from the equilibrium position, that is L by 2 into theta. So for this spring also it will be extended by L by 2 into theta. So the spring force will be in this direction, and the spring force is K and the spring force is K into L by 2 into theta. So restoring torque for the second case, that is minus I theta double dot, because I is same for both the cases. So I theta double dot is going to be K into L by 2 into theta into the length or the distance, that is K L by 2 into theta, and the distance of the point of application of the force, that is L by 2, plus K L by 2 theta into perpendicular distance of the point of application of the force, that is L by 2. So ultimately I am getting K L square by 2 theta. So theta double dot I can write, minus I will come in this side. So for the second case I am getting omega 2 square to be K L square by 2I. So I can write omega 2 square as 4 pi square f2 square K L square by 2I. Now if I divide the first equation by the second equation, then I will get f1 square by f2 square, and if I divide that I'll get 5 by 4 by 1 by 2, so I'll ultimately get 5 by 2. So f1 by f2 I have to find out. F1 by f2 is root over of 5 by 2, and that is matching with option C. So option C is our correct answer. Okay, we'll go to our next question, question number 4, and let us read the question. Consider a star of mass m2 revolving in a circular orbit around another star of mass m1 with m1 very greater than m2. The heavier star slowly acquires mass from the lighter star at a constant rate of gamma kg per second. In the transfer process there is no other loss of mass. If the separation between the centers of the stars is r, then its relative rate of change 1 by r into dr dt is given by. I have to find out the value of 1 by r into dr dt. So let us draw the diagram, small diagram first. Let's say this is a bigger star that is having mass m1. There is another star of mass m2 that is revolving around m1, and what is happening is the bigger star is slowly acquiring the mass from the lighter star. So there is some rate of change of this mass m1 and m2 both. So it is gaining mass at constant rate gamma kg per second. So dm1 by dt will be gamma, and let me tell you it is plus gamma because it is slowly gaining the mass. So change is positive. Similarly, the lighter mass is losing the weight. So dm2 by dt or rate of change of this mass is minus gamma, and also is given that m1 very greater than m2. Okay. So as it is getting mass from m2, it is slowly becoming lighter and it is slowly becoming heavier, but as m1 is very greater than m2, that change may not be that much visible. but for this M2 mass, it is light mass and it is losing also mass, so it is more visible compared to M1 mass. So let us assume that at any instant the speed of M2 or the revolving speed of M2 with respect to M1 is V. Then what we know, that is M2 V square by R, and at that time let's say the distance between these two masses, that is R, and we'll see the mass M2 from the center of mass M1, then it is revolving and it is getting on a centrifugal force, that is M2 V square by R, that will be equal and opposite to the gravitational attractive force, that is G into M1 M2 by R square. Now for that instantaneous equilibrium, I can write that G M1 M2 by R square will be equal to M2 V square by R. Then I'll get the value of the speed, that is V root over of G M1 by R. And see, as M1 mass is gaining the mass and M2 mass is losing the mass, there is change in the gravitational attractive force, because M1 M2 both are changing in nature. So this force, that is Gm1 M2 by R square, that is also changing with time. But this change of the force that is happening centrally. So there is no external torque in this case. In this transfer of mass process, there is no external torque. So what will be constant? The angular momentum of this mass will be constant. So what is the angular momentum? M into V into R. So M2 into V into R, that is the angular momentum, that will be constant. Now we can put the value of V, M2 into root over of Gm1 by R into R, that is constant. So I can write M2, G is a constant term, so we'll make another new constant, that is root over, we'll divide the constant by root over G, so it will be constant. So into root over of R, that is constant. So I can take log both sides. So ln M2 plus half ln M1 plus half ln R is ln constant. So if I differentiate, I'll get dm2 by m2 plus dm1 by 2m1 plus dr by 2r is equal to 0. Now if I divide by small time dt each and every term, I can do that. So see, I am getting dr dt into 1 by r term. So what is that term? Let us express in terms of other terms. So half of dr dt into 1 by r, that I am getting minus dm2 by dt 1 by m2 minus dm1 minus dm1 dt 1 by m1. So there is another 2 you are getting. But see, this term I can write dm2 by dt term, I can write minus gamma. So this minus gamma, if I write, I'll be writing this minus dm1 by dt is plus gamma, so it is gamma by 2m1. But see, as m1 is very higher, so I can ignore this term and I can consider it is very close to 0. So entire thing what I am getting is gamma by m2, that is half of dr dt into 1 by r. So value of dr dt into 1 by r, that is 2 gamma by m2. So it is not matching with any of the answers. So none of the options are correct, but the one answer is given, that is minus 2 gamma by m2, that we can tick, but that is also not correct answer. That is also not correct answer, but we can tick at least, because the mod value, it is ultimately this one. Now why this option, that is minus 2 gamma by m2, is not correct? because now let us assume, see what this term represents. At any instant, if the distance between these two masses is r and the rate of change of the distance is dr dt, this term will be positive or negative. That will depend upon the force of attraction between them is increasing or decreasing. So 1 by r at any point of time, let's say it will be positive only. So if the distance between two masses is increasing, this term will be positive. If the distance between two masses is decreasing, the entire term, this sign will be negative. Now let us analyze whether the distance between two masses will be decreasing or increasing. Now let us take a very small mathematical task, that is, let's say one mass is 100, another mass compared to this mass is very less, so let us assume it is 2. Now let's say after small time this mass is reduced by 1 kg, so it will become 1. This mass will be increased by 1 kg because that mass will be acquired by this mass, bigger mass, so it will be 101. Now what is the attractive force initially? It will be proportional to m1 into m2, right? So what is m1 into m2? 200. The second case, if the attractive force between them is proportional to m1 into m2, that is 101 into 1, that is 101. So see, the force of attraction between two masses is decreasing in this case. So as the force of attraction between them is decreasing, the distance between them should increase. So dr dt term should be positive. So ultimately we are getting the positive answers only, but in the question it is given minus, so it is not a correct answer. So it should be positive.
As the distance between the two masses is increasing, let's say this is m1, this is m2, the possible trajectory of m2, maybe it will be like this. It is constantly increasing. So compared to here the distance will be more, here the distance will be more. So continuously it is increasing. Then that is the possible trajectory. Possible trajectory of mass m2 with respect to mass m1.